Hi, I'm Alfonso Lagares, a student in Professor Fenton's Physics 2211 class, and this is my Lab 4 report where I will be studying the oscillating motion caused by a spring. This lab focuses on springs, which experience spring and gravity forces. The spring force is a restorative force experienced by objects attached to a spring that is proportional to the deformation of said spring. The deformation can be both negative and positive, meaning that the spring can be either pushing or pulling the object. The spring force can be calculated using Hooke's law, which assumes that the spring force is directly proportional to the deformation through a coefficient usually called K, that is specific to the spring used. Moving on, the law of conservation of energy states that in a closed system, meaning that the system is not experiencing any external work, the total energy of the system is always equal. This means that energy is not created nor destroyed, but simply transformed from one type of energy to another. In the case of our spring, energy can manifest itself in three different ways: as spring potential energy, gravitational potential energy, or kinetic energy. By calculating the three of them for every point in the simulation, we expect to find that the total change in energy of the system is zero. Understanding these two concepts is extremely important, as many microscopic and macroscopic motions can be closely modeled using Hooke's law and the principle of conservation of energy. For this lab's experiment, we recorded the motion of a spring that was moving in the XY plane. We hung a 0.2 kilogram mass from the end of a spring that was itself hanging from an aluminum fixture. We dropped the weight from a known initial position, trying to give it no initial velocity. The mass was left to oscillate freely for a couple of seconds, and both its X and Y position were recorded for every moment in time using Tracker. Going on to the model, I created a GlowScript script that simulated the forces acting on the mass and the spring as it oscillated. I defined a few initial conditions for my system. The mass of the whole mass spring assembly was recorded to be 0.2 kilograms, and the spring constant was measured to be 8.63 newtons per meter. The relaxed length of the spring was 0.106 meters. This value will be extremely important when calculating the spring force experienced by the mass. The initial position was pulled from the experimental data, and the initial velocity was assumed to be zero, as the mass was dropped from rest. I also assumed the system was closed, meaning that the total energy in it was not changing. At every iteration of the simulator loop, I calculated the spring and gravity forces that the mass is experiencing. The force of the spring is given by Hooke's law, and it is proportional to the spring's deformation from its original length. The net force is then calculated by adding these two forces. The acceleration, velocity, and position of the mass are then updated using the equations of rectilinear motion and Newton's second law. After this step, the different energies present in the system are calculated. The kinetic, potential gravitational, and potential spring energies are calculated and then added up to find the total energy of the system at every step. The result is this animation of the mass oscillating with the spring and three graphs. The first one depicts the change in energy of the system for each type: gravitational potential, spring potential, and kinetic energy, and two graphs depicting the X and Y positions of the mass at every point in the movement. The blue line is the simulated motion, and the red one is the experimental one. In conclusion, the model was somewhat accurate at predicting the position of the mass as it oscillated. The X position was much more accurate than the Y position, probably because the Y movement had the extra effect of gravity involved, which increased the error in my measurements. Furthermore, it is clear that the experimental data is noisy, which makes it harder to predict. Using a better camera and a more stable experimental setup would have improved this. Not only that, but there seems to be some systematic error in the simulation, probably caused by errors in the initial conditions. A better measurement of mass, the spring constant, or the initial velocity of the system would have improved the model. It can also be observed that in my model, the energy principle is satisfied. The total changes in energy cancel out, meaning that the energy is only being transformed and not actually leaving or entering the system. This means that energy is being conserved, and thus the total change in energy is zero. Finally, the X and Y oscillation periods can be measured using the X and Y position graphs and come out to be 1.3 and 1.1 seconds respectively. I believe the shorter oscillation periods in the Y direction is likely due to the force of gravity, as it constantly pulls the mass downwards. This makes the mass oscillate faster in that direction than in the x-axis, where only the force of the spring pushes it to move.